Hello, everybody. Uh, I don't know where you are. For me, it's morning. Wherever you are, enjoy the day. This is a lecture that we prepared in Certora to introduce uh, audience to formal verification. It's meant to audience without a knowledge in formal verification, but developers. We really encourage participation in the presentation. Also, we have been building a new product, which is a leverage form verification and AI together to make form verification easier, which is called AutoProver. It also has auditing and other cool features. We will provide credit for usages, so for usage of the tool, because the tool actually does cost you to use the LLM. So we will provide credit. So please register. Even if you come late to the lecture, please register. So quick question, are you able to see my screen? People on the audience? Okay, nobody is, okay, good.
Yes, Mooly.
So, I think before we dive into formal verification, I want to explain why actually formal verification is relevant now. So I think it seems that with the age of LLM, we used to, when I started computer science, you can see it's a long time ago. Well, we had software which is called safety critical. This was software using in airplanes and in missiles. This was very, very unique and important, and people did not change this. But nowadays, it seems like a lot of code becoming safety critical, even libraries, graphics, LLM implementation themselves, they're all safety critical. And in fact, also software used to be developed by skills individual. Now it's developed by LLM. We are working in the domain of Web3, which auditing is a standard which improves security, but even auditors and LLM are unable to find the new bugs. And of course, LLM models are getting better all the time. But this is a double-edged sword because basically every new LLM model, whether it actually can trigger different bugs, and it's not clear that the developers can keep up with the rate of bugs found by hackers. And this is even getting more and more worse once code getting more complex. So the question is, who can stop it? LLM are doing good job in improving, but in LLM, the notion of correct is not well defined. And in fact, this is the most thing we hope to get from these lectures, to understand the concept of correct. There's excellent material in form verification, but in this lecture, we have tried to make it so it's giving you the beauty of specification. What does it mean, specification? And most of this lecture, I try to be very informal, and I want you to actually participate. It's the idea of what does it mean to have informal specification. Okay, so I want to start by two myths in formal verification, which there are many. Formal verification is a mature field. But I think when I studied formalification, even up to the last several years, I've heard people are saying that formalification really is hard and it requires PhD, and we have a lot of excellent PhD in formalification. But I think what we want to think, and I actually seeing it happening already, is that we are seeing more and more people getting into formalification without PhD in formalification, without even studying formalification. And of course, AI is a big part of it. The fact that software is evolved is a big part of it. And I think this is what we want people to do. We want people to use formalification as early as possible, integrate into your continuous development, and write specification early, and use testing and formalification very early in the process. Another thing, which is a very common misconception that people say, I formally verified the code, it has no bugs. And I think this is wrong. We have seen it many times. Because formal verification, and that's actually the purpose of this lecture, is actually shift the problem to the formal specification. And the issue is that formal verification, you want actually the specification to be interesting, to make the formal verification interesting. And this is what we're going to try to do in this lecture. I encourage you enter this field to do it, and also LLM could be useful there. So the question is, how do you write a good spec? I'm going to show you very, very simple examples, but there are a lot of other examples in the literature. I encourage you to look at them. So in this lecture, I'm going to start by explaining what is formal verification. I'm going to use a very, very simple example of bubble sort. I will write complete specification, start actually informal, and then talking about formal, then explain briefly what are techniques we have for formal verification. I'll basically explain what are the interesting challenges in formal verification. And finally, I will introduce our new product called AutoProver, which is a version of LLM with formal verifications. Combine both, and it's agentic, it's open source, and you can use it. And as I said, you will also get some credit to use it to try this tool. And this tool, by the way, can be applicable for formal verification of smart contract, but it does audit on arbitrary code. And you are encouraged to use it on any software that you have. So this is taken from the literature. Formal verification is the act of proving and disproving correctness of correctness of code. In particular, we want to mention the fact that it's not just formal verification, it's also bug finding. So you take both correct and incorrect system, and these are evolving systems. We are trying to prove that they behave correctly. So formal verification has a rich history. This is part of it. It's going back to the origin of computer science. Turing, the inventor of the computer, Turing actually came with this idea of sort of machine-checked proof. And then there was what I want to call the golden ages, actually starting in 70. I'm old, but not that old. But these are the people that actually did many, many seminal work. And I mentioned Robin Milner and Tony Hoare, Edgar Dijkstra, Patrick Rousseau, and Robert Floyd. All of them laid the groundwork for formal verification. At that point, people really thought that formal verification was useful, and actually even, especially in academia and industry, there was a lot of enthusiasm for verification. And then in 1979, one article came from academia, but this article was very, very bad for verification. I think I encourage everybody to read it even now. And this article by the DeMillo essentially explained why formal verification is hard and will not work, and a lot of things. So this is actually where the dark period of formal verification starts. Interestingly, this is where I actually started my career in computer science. So basically, at this point, people were thinking formal verification is too hard and not useful. And then there's 25 years of very hard work, where a lot of people, including myself, were working very hard to build technologies like SMT, tools like Z3, EIX, other tools, also tools like dependent type-based, ROC, of course, recently Lean. So all of these tools make formal verification easier. And we see actually that the quote of Bill Gates about the work of the Microsoft research, which I contribute some algorithm, you see that actually all of these things became more natural. And we think that now with the LLM, formal verification getting much more easier, and that's why we think that formal verification would be more useful. By the way, this happens in many fields of computer science. You start with a hype, same thing with AI, and then people realize there is a reality, and finally comes the practical part of it. So we are now in the practical area of formal verification. So one way to think of formal verification as opposed to other methods like auditing or fuzzing or any kind of testing, that formal verification is something that really increases your confidence in the code. So there is something that you know about your code as a developer, and there is a question is what you don't know about your code. And basically, formal verification helps you increase your knowledge on your code. You write this spec, and these packs are able to find even bugs that you didn't perceive in the code. And I'll give you an example, but this is the beauty of form verification, that you come up with properties that you write about the code, and then you check these properties. So in fact, you see already that specification or this idea of properties are essential in form verification. So let's start by the simplest program, and I encourage you to participate. But this is the simplest program I'm going to use at the first part of the lecture. So this is bubble sort. I'm sure all of you know it. It's a very, very simple sorting algorithm. It bubbles the element. So you have a list and you are trying to sort it. It's not the most efficient algorithm, but it's enough for this lecture. So you start with the array. You see in the first iteration you bubble 5. So you basically compare compare consequent element and swap the element, and you bubble 5. The next you bubble 4, and so on. Every iteration you actually bubble more element until the array becomes sorted. So here is the code. It's very, very simple, taking from the internet. You have two loops together. You see the outer loop start at the length, and in the inner loop, you do the swapping. Every time you do swapping, you record if the swap was correct or not, because if you had one iteration that everything is in order, you can optimize. You can finish early, and then the simple swapping that swaps the adjacent element. So what properties do you think sort should have? Maybe I love for somebody from the audience, if you can just tell me what are the simplest property of a sort that you expect? The simplest, the most natural, everybody understand. Yes, Sachin. Yeah.
The length of the array will always be the same.
The length of the array will be the same. That's a good property also. But what's the property related to the order?
At the end of the loop, like it will always be in either descending order or ascending order.
Fantastic. So you see here, the element, so I choose the ascending order because this is how it goes. And another one is termination. So these are sort of very simple properties. And what we'll see is that even if we start with these simple properties, existing system can find, including the system that we develop and others, they can automatically identify bugs in the code without actually knowing what. So basically, these are if you write these properties, and here I'm using an informal way. Later we'll write it in a formal way. But all the elements are sorted, and it's always terminated. So this simple property captures many bugs, actually. Not all of them. We'll talk about it later, but it captures many bugs. So let's take an example. Here's and I basically took LLM to find this bug, but you can also find it. So this is a very simple bug here. You see that it's a bug that, in fact, form verification tool can capture, it can find using the properties. So you see here that there is a list. And so this is a particular example. Form verification does it without, of course, knowing the input. But this is one input. You see 972, and you see that at the end you have 792. So this is a bug which is captured by the formal verification. Can you tell me, look into the code and tell me what is the bug in the particular in this bug in this code that caused this violation? What is wrong in the code? Why is this violated? What is wrong? What is wrong in this code? Somebody want to? Yeah, you can unmute yourself because I don't see you. Or if you're well, can you mute people because I think they can't answer? Unmute. Sorry.
Yeah, but they can unmute themselves. They are writing on the chat, Mooly.
Okay, but I am unable to see. That's hard. That's why I prefer. But
Yeah, the loop is running till the n minus 2. I think
exactly,
it should run till n minus 1.
amazing. So this is but it's a common bug, even this. So inner loop. So there are two loops here, and the inner loop stopped too early. So that's a mistake. You see that. Great, thank you. What about this bug here? This even maybe simpler, but still bug. You see that here in this bug you have 792, and it's 729. So what's the mistake here? What is the mistake in the code? Why is this bug detected? Why is this bug detected? What's wrong in this code? There's something in the chat, but I'm unable to see.
Eugenio says, I should start from 0 on the chat.
No. No, it starts correctly because look, it's if you start from 0, you go to -1. You start from I1 because you are comparing the elements start from 0, but you're comparing the I -1 to I. So it does start
Swap
correct.
never get through.
Amazing,
Swap never.
amazing. Yeah, exactly. So swap flag was not updated. It's a simple mistake, but but again, the algorithm doesn't know your code, it knows, and this form verification, we have this property, and we also don't know, you notice that we don't know what kind of bugs will happen. We just know the desired property. So these violate the desired property. So this is the idea. And I want to summarize, even though this is a very simple case, there are many very clever implementation of sort, quick sort, radix sort, all kind of things, insertion sort, all these sort, other kind of sort. But in fact, this simple spec captures many of the mistakes. So the question I have for you, is it enough? I mean, we already mentioned that the length must be maintained, but are there other properties or maybe another word? Suppose I only check that. Can I guarantee to our client that the code is bug free? Is it the case that all the bugs are captured by this spec? Or that's the question for you. So this informal spec, does it capture everything? Sachin, you want to help us, yeah, want to help us here? So, what do you think? Is your intuition is that spec complete? Is that spec covers everything? And you don't need to refer to any form, but does it cover everything you want here? Does it cover all the desired properties? Does this spec cover all the desired properties?
I guess no.
Great. No. So, what is not covered?
So basically, we have covered only two properties. Like the length should be same, like earlier one guy told. And checking the output will also like checking that the output will always be in ascending order. Whether the variable are getting added or not later on, like the whether the values remain same or not. That can be also one of the property.
Amazing, amazing. So in fact, here is a simple bug which is not captured. It's very simple. It's a mistake, probably a very initial programmer mistake. You see, somebody didn't use a temporary variable in the swap. It's a very basic. So you see, the swap itself just so basically you see you take 729, and because you do the swapping wrong, 7 and 7 are there. So the array is sorted. So in fact, if you look at it from a sorted and you prove sortedness, you get a formal verification that sorted is correct. But in fact, it's not enough because you lost the two elements. So that's not the case. So this bug is not captured, and other bugs could be not missed. So basically, the idea is that here you broke this, there is a mistake. And in fact, this brings you to the complete specification. And beautifully, for the sort, we have a very, very simple specification. So sorted, we already discussed. Termination, we already discussed. Another property is inbound. You don't want to go out of the memory. You mentioned the strength, the length, but in fact, and this is the Ionisni also mentioned it. Basically, what we want is a permutation. We want the original list and the list at the end to have exactly the same element, just in different order. Another property that we want, because usually we don't execute it we can execute it in a different environment. We don't want to affect other part of the storage. You don't want to affect anything else. If you have a code, usually this is invoked in some way, and you don't want to affect it. So you want to make sure that you're not changing it. And the last property, probably the most tricky, but still relevant in many systems, is stability. You don't want to swap element unless you have to, because usually you are checking based on one property, but you have other desired properties. So for example, you are sorting people according to their first name, but maybe you have last name, or maybe you have income, maybe you have another property. So you want to maintain stability. It means that if two elements are in order, they are not swapped. Okay? And the claim is that once you enforce this, and I challenge you, actually, it's not something I prove, but it's something I believe, you in fact find all the interesting bugs in any sorting. So you enforce this, and instead of checking for bug, you check for this property and you formally verify. Of course, you can fuzz it or test it, that's also useful, but you can formally verify that the code obeys that. This means that the code will not have all the unknown errors which are implied by this. So let's take another bug here. This is a bug which is, does anybody see the bug here? This is a bug which is captured by this specification. But what bug is here? It's a bit subtle. What bug it is here? It is also a bug that, again, I got from chat, but it's a, but what bug is here?
Yeah, in this one, loop is running till n. Like it should run till n-1.
Exactly. So there is a memory error, and this is going out of bound. And again, because we are checking bound, we are able to prevent these kind of bugs. What about this bug? You see already the thing. So the bug here is that the order is not correct, and in fact we are getting this. This is more tricky. This is more tricky. Watch the bug here, and just to make it clear, we wrote just the number, but also the names. So what is the bug here? And what property is violated? What is the bug, first of all? What's wrong in this code? Does anybody see? Is there something wrong in this code?
It's not stable, is it?
Exactly. It's not stable. But why is it not stable? What's the mistake?
Greater or equal?
Greater equal, right?
Exactly. So the mistake is the greater equal instead of greater. So this is bug affects the stability. So thank you. So the idea is, you see that when we enforce these properties, we can check the code, and we can guarantee that the code has these properties. So here you see the importance of stability. It prevents these kind of bugs, and we usually check all these properties when you do formal verification, And in this case, we get the code right. And the most thing I want you to take from I want you to get from this is that the most important thing for formal verification is get the specification. So in this case, I only show you the informal specification, but you see that there is complete informal specification. Okay? So that's the idea, is you swap equal element, and it's sorted, but it violates the stability. So how do you write formal specification? That's a topic for many lectures, and here I'm only showing you the way it is done in the Certora prover, but the other system that have. So the idea is that in Certora, what we really want, we want the specification to be external in some sense. We do not want to write a specification in the code, and this is a decision we made because we wanted to make the verification so that it's reusable, and we want to make it high level as opposed to low level. I talk about other system. So here you see how we specify the sortedness. The other properties are more complex, for example, stability and others. But you see how it goes. We call the sort. It's essentially some kind of harness for testing that you would think. We call the sort, and then we write assert, like you write an assertion in programming language. But here you see we do something which is not usually expressible in programming language, and it shouldn't be. You write quantification. You write for all. This means that for all element I, if I is between 0 and n minus 1, then the elements are in order. You noted that this is actually not something you write in code. You can think about it like a conjunction or a logical AND, but it's logical AND of all the elements. Of course, it's not meant to be implemented, so we are not enumerating all the integers or whatever. It is actually just a mathematical specification. So it's something that we convey the prover that this must hold. Okay, and it's not intended to essentially test it. It's intended to check it and intend to formally verify this property. It's not something that we are enforcing at runtime. It's something that we are checking before the code is delivered. So this is a property that we check. So in fact, for example, for this to be violated, it's enough that there exists one element I that is actually not in order. And the same for other properties. So we write this assertion. We try not to modify the code. And this is how we write formal specification. Certora prover has many ways to write this kind of formal verification. There are a lot of other excellent tools that do this kind of things. That's the idea of formal specification. So we go from the informal claim, which we saw, which was in English, into a formal claim in some language. The other questions so far before I continue? Okay. So let's talk a little bit about the formal. I will be able to, before we jump to our own tool. So there are a lot of work on formal verification and excellent material. And there are two approaches, and both of them are very useful. So the first one is called proof assistant. Sometimes people call them interactive term proving. So the idea is that in these methods, you are not actually thinking about the program. You are thinking about the proof. The center of the thing is the proof. And this is a domain-specific language for writing proofs, like you write in mathematics. But unlike the handwritten proofs, they are checked. You have a mechanism that actually guarantee that you cannot write a wrong proof. It's usually based on some theory. The most commonly used is dependent types, but it's based on some theories that essentially don't let you get things wrong. Okay, that's the idea. And it actually is not even limited for programs. You can use it, and people are using it, you've seen in the literature, to prove mathematical theorems. Okay? And where does the code comes into play? The code is an artifact of the process. So basically, as the part of the formal verification, since it's constructive mathematics, we can construct the code. So this is the idea. You start from the proof. There's this assistant. Sometimes it's used tactics or other way to make this proof easier. And if the proof succeed, we can extract the code. There are tools like Lean4, RAC, K, Isabel, Miranda, these are tools that are HOL. These are methods to do this proof assistant. They are very useful, and they become now more useful in the age of LLM, because LLM can help you with manipulating this proof. You can ask the LLM to do many things, and it can do it. So this is the proof assistant. It's a great method to prove code, especially new code. The problem with it is that if you have an old code, it's hard to apply it. Also, it's limited programming, because some things, it's basically you have to go for mathematics, and something like concurrency, distribution. There are people doing progress there, but it's much harder. You'll have to do many, many things to go into this domain. So this is one approach. The other approach is called program verifiers. The idea is that you actually center around the program. And this is, of course, for formal verification of program, like we've seen in the sort case. So basically, the idea is you annotate the program with claims. If you want to think in terms of mathematics, in the proof assistant is essentially very general mathematics. Here it's a very it's a special case where you prove things by contradiction. You're trying to derive a contradiction. If you are able to, you found a bug. If you're unable to, you actually can generate a proof using resolution or others. You can use you can generate a mathematical proof that the program behaves the same. So both program methods here generate proofs. The proof assistant is unable to generate bugs. The program verifier is able to generate bugs. The idea is to compile the program into spec into constraints. It tries to solve the constraints. If it finds a solution, the solution is a bug, or what we usually call counterexample, because it's actually not necessarily a bug in the code. It could be also a bug in the spec, of course. So you see here that there are tools like CBMC, Verus, Y3, Viper, and our AutoProver. They have some difference between them, how they handle loop, how they handle recursion, but this is similar. They're all similar ways. This method has been shown to work the verifiers on all levels of abstraction, on executable, on bytecode like the AutoProver, on source code like Y3, on Verus, on Rust. So all of these things all of these levels are supported. The limitation of program verifiers, because it's the limitation of constraint solver, it could be computationally expensive, and also there could be some things which are hard to prove automatically. In the case of proof assistant, the human is on the loop. In the case of program verifiers, it's sometimes hard because the human needs to understand the level the program verifier works. And in the age of LLM, both methods become more easier. Both methods, people see LLM is doing a good job for both of them. It can help the verifier, it can help the proof assistant. When we are seeing it, and other teams are seeing it, LLM is making all form verification easier. Okay, so let's start with go with our example. So you see here, our example applies to bubble sort with the help of one of our engineers, John Thoman. Basically, you see that, in fact, and big help from our friend ChatGPT. So you see, actually, ChatGPT was able to take from the internet and generate a proof for this bubble sort. We came with a property. So you see that, in fact, you don't see the code here at all. You see a mathematical definition. Maybe it's a bit hard to see with my screen, and I'm going a bit too fast, but there is an inductive definition of sortedness. It comes with some definition of sortedness. And then there's a theorem you see about permutation. So in fact, you start with the properties. You start with the properties. And there you derive, and in fact, the proof is pretty large. The proof is pretty large. You can start reading it, but it's pretty complex and pretty large. But the nice thing about it with LLM, it can actually generate the proof for you. So even though the proof is large, obviously if you write this proof by hand, it will be a bit shorter perhaps. But the idea of this, you have a proof which is checked by machine, and it generated, in this case, automatically by LLM. And in fact, this is using Lean 4. which is a state-of-the-art formal proof assistant. You can do it with other proof assistants. Okay, question about this so far? Yes, Sachin?
So, Professor, can we, if this proof is generated by LLM, but we still need to verify this, right? Because it can also just try to reward hack or just make it past the verifier without being correct itself.
The answer in general, definitely yes. But here, since we came with the right properties, we know. So the idea is that, of course, you can argue that maybe there's a bug in Lean 4, and we have seen recently, but I don't think I would worry about it. I think the issue, the biggest bug in form, so of course, there is a trust level on the formal verification itself, whether it's based on proof verifiers like ours or Lean 4, but I wouldn't worry about it so much. I think the biggest bugs that we have in formal verification tool is the specification. So I would tell you, if you know that you have the right specification, I would be less worried about it. The problem, of course, that yes, in real system, coming up with specification is very hard. But in this case, since we agreed about these 6 properties, so if you formally verify the properties, I would be okay. So here you see, so if you are checking it with Lean, the only thing that you need to check, so this proof is huge. You don't need to check it. But what you need to check is that the definition of the sortedness and the permutation is correct. So the answer, yes, you need to check, but you need to check the specification, not the proof. Because this tool is sound and it's actually, we are seeing, I can tell you in Certora, we are building very complex software, but we have seen, and of course we miss few bugs, but we never miss bugs due to technology failure or maybe very hard. The bugs that we miss is due to the fact that we don't write the right spec. That's the biggest problem for verification. So if you trust the spec, I would trust the proof. The issue is that trusting the spec is hard. We can use mutation testing, we can use review, but in this case, the spec is here, and you can check it, and basically assuming that the informal spec is good, then it's good. But of course, informal spec could be wrong. I'll talk about it later in the last part of the lecture. But I would think this is doable. So the answer is yes, you need to check it, but in the case of Lean, you only need to check this first screen. All the rest of the screen, which I haven't shown you, which are huge, which is the proof, it's a bit unpleasant to read, but you don't need to read it.
Got it. Thanks.
Okay, but what happened when you apply
Can I ask some other
Sure.
question? Sorry.
Sure.
So, hi, Mooly.
Nice to meet you. Long time.
Yeah, nice to-
Yes.
Yes. So this doesn't come from code to proof. It goes the other way around, right? So essentially, you can look at the proof and then generate code out of it. But so if you want to go from code to proof in the Lean setting, you have to trust the translation of ChatGPT into Lean, right?
Correct. So the question is, how do you actually go from code to proof? So because Lean is not even meant to be from code to proof. So there are different people doing different things. I think there is Project ANEA, which is coming from the semantic of the program and try. So going from code to proof is difficult in these systems. One way to do it is to try to define the semantic and try to do so. It's in general very hard to go from code to proof. These go from proof to code. That's the beauty of this thing, but it's also the limitation of it. But you are saying, look, I have an existing code. How do you deal with it? And the question is, there are different ways. There's a trust issue, but it's not also trust issue. There's expressibility issue. How do you know that what you have, I have a program with side effects. How do I know, for example, I have a Rust program which is not necessarily type safe. I won't be able to convert to this. So there are inherent limitation. You can use the LLM, but the LLM will cheat. There are inherent limitation of going from when you go with tools like Lean from code to proof, it's much tricky. There are some people trying to do with the semantics, but you're absolutely right. Here I'm assuming that I go from proof to code. This is the standard thing. But with the other system, I'll show you with the proof verifier, of course, we go from code to proof. But you're right. You're right here. And of course, But there are systems like Canea, and also LLM, of course, can do many things. Maybe you can try to do some pattern matching and see, but there are some issues. There are some issues, there are conceptual issues, how to verify existing code with assistant, especially if this code is not expressible. Usually the way people, when they use interactive term prover in industry, they rewrite the code from scratch, which is a good idea, but not always and not always possible if there's some features that you cannot support, or the semantic is not very clear, or some other things, right? Okay, thank you. So what happened? We applied. So we took here the incorrect bubble sort. So the good news is, of course, that because Lean is sound, it was not able to verify it. But how does the programmer understand the bug? And that's the beauty of program verifier. So if you have a program with a bug and you run interactive term proof assistant, it's just going to die. But I don't know. I mean, it could be that it just died because the proof is too hard. You don't have any way to diagnose the failure. And this is and whether you use LLM or use human, it doesn't matter. It's very, very hard to diagnose failures with these tools. So if you know what you're doing, it's great. And of course, LLM can help you but still, if your program is buggy, it's not very clear that it's really a bug in your code or just that so basically this is a limitation of proof assistant. I took a tool like CBMC. Of course, I could use our verifier, but I took CBMC. It looks more appropriate. So CBMC is an excellent tool, one of the earliest verifiers. It's Go and C code, which is lovely, or C++. It models the exact semantic, which is beautiful, but it's a bit low level. But the interesting thing is that it was able to give you a trace. It's not so easy to read. And with our tool, we did spend a lot of time making the counterexample easier to understand. So you see here, there is a low-level trace. It's a bit big, but it indicates the bug. And if you look at it, it will actually show you, and you are able to find the bug from it. It's a bit big. Here you see things which is more readable, like we do in Certora. You see here, we get this for all, and then the tool will give you an example. So this, you see, it gives you the concrete failing. And this is something that we can do in Program Verifier, and it's impossible to do with a proof assistant. So it's basically giving you the ability to find bugs, and these are corner cases. This is what we have done with Certora Prover now. We are finding bugs which are sometimes very even hard for us or for very, very strong auditors or fuzzer to find. Basically, you are finding rare corner cases where the spec is violated. And of course, here there's no trust issues at all. You find this bug, and once this bug is there, you can run fuzzer, we have seen people using our tool, and after that, using fuzzer, it's excellent. You can actually find the bug with the prover and then run fuzzer and reassure that this bug is real. So far, questions? So basically, I show you two tools. And I just gave you the beginning of feeling of them. One of them is called Proof Assistant, and the other one is Program Verifier. They are complementary, and they have complementary strengths. I encourage you to use them both. Okay. Yes, there's a question by Sachin before I go to the last part. Yes.
Yeah, sorry. How is it checking the counterexample? Are we doing like state space checking, or is it like fuzzing, some sort of PBT fuzzing?
So first of all, it finds the example without doing any fuzzing. It finds the example by doing mathematical reasoning. But once you have this example, you have this concrete failing, you don't even need fuzzing. You can run essentially the input and the output, okay? You see that it gives you, like if you run this Certora Prover, it will give you an example. It depends, because sometimes this example is not real, because it could be not real for two reasons. One, the spec is wrong. So in fact, or that it basically what we call inductive claim. It starts with a state and goes to the next state, and this state is not reachable. But the idea is this one you can check with fuzzing, or you want to check that this state is. So for example, here, it gave you this concrete example. It tell you, I start with 972 and I get 792. Okay? But if this, maybe this is talking about a big program, and this 972 state is not even feasible. Okay? So this you'll have to do testing. But the beauty of this kind of method is that, and this is the beauty of program verifier, it gives you an input. It gives you what we call concrete input. It gives you a violation. That's why the program verifier are much easier to diagnose, especially when you have failures. Make sense?
So we are doing, yeah, so we're doing like state space checking for these, like
But
all these
first we get this number, and then if you get this 972, in this case of the sorting, you can essentially run the program and just put this, and you put this array as the input of this sorting. Okay? It could be the case that this sorting, for example, is part of larger program, and then you'd have to somehow trigger the input so that it gives you this input. So you'd have to do some kind of fuzzing or anything to go into this state. Make sense?
Yep. Thank you.
Jochen, do you want to add something, or Jochen is or Julian, people from our team who are okay. Thanks. Okay, so now I'm sort of in the third part of the lecture, which I basically want to talk to you about what we did with this AutoProver. But I want to actually sort of higher up and try to explain something that, even though it's obvious, for me, it took many, many years to figure out. So there are three, and I think even if you look into this bad article saying that formal verification is bad, it's not, and which is a beautiful article, I really recommend. So there are three fundamental problems in formal verification that I think a lot of people don't get, and I think it's important. What is hard in formal verification? So there are three things which are hard. The first thing, we see it in this sort. We came with these 6 properties. How do you write these 6 properties? And in the case of sort, it's of course obvious, but in complex system, so how do we know what informal specification a system must have? The second one is, once you have this informal spec, how do you convert to formal spec in our language or in Lean or in that? Doesn't matter. And the third one, once you have a formal spec, how do you disprove or prove the spec or use fuzzing, or how do you do that? So basically, these are 3 separate problems that you need to solve them all. So maybe I encourage you to answer, which one is the hardest in your opinion? I mean, which one, based on your intuition or your experience, which one is the hardest?
Writing this back,
But which one, the informal or the formal?
the informal.
You're right. You're right, and it took me a while. Where do most research in computer science, including my own, falls into? Which of them? The 1 or 2 or 3? Where do most people spend research and
The
publication?
second and
No,
third.
the third. Only the third. Only the third. Only the third. You can argue that we wasted our time, but I think the third is because that's where you get academic articles, that's where you solve open problem. So the third one is basically, and that's actually where tools like Lean4, Certora, this is actually where we do a lot of work, and I must admit, we, of course, our colleagues in the last 3 decades, we made a lot of progress. So the third one is where a lot of research has been investigated. The second one is actually where LLM is helping a lot. LLM is helping. We can see with AutoProver, LLM is helping with the second one. Going from informal to formal, of course, humans still need to check it, at least for now. But going from informal to formal, that's what we'll see with AutoProver. It's actually where this is, LLM is getting better. And it will get better in time. It's very clear. And the first one remain and probably will remain the hardest, sort of taking a complex system and coming up with the informal properties. And this is sort of the hardest. We are making baby step with AutoProver, but it's still very hard. Okay. So let me go to AutoProver. So AutoProver is essentially trying to solve all of them, but obviously it needs most of the help in the first one. So what does it do? It starts by the design. It's actually looking into design. At the moment, it's trying to understand what is in the design is amenable to formal verification or even to auditing. And then it has what's called audit agent, or you can think about it like pen testing. It tries to find bugs in your code. There are other tools like this, and there are many other tools, both in Web 3 and outside in Web 2. But the idea is that this is connecting to the design and trying to find what kind of bugs is there. Okay, and this is this audit agent. Then there is formalization. We come with properties, so we take the informal properties and try to formalize them in our language and other language. And then we run fuzzing because we think that fuzzing is cheaper than formalification. And we think that in fact it's more intuitive. At the moment we use Foundry, but we are now integrating other fuzzers for us. So that's where we do the fuzzing. And finally, we do formal verification. At the moment we use Certora, but we do plan to use Lean and other methods. So the idea is that these all together, and of course, all of them are leveraging LLM. All of them, they are different agents, and you can actually configure, and it's open source, so you can in fact use your own LLM. But the idea is you have agent for everything. Of course, you can use different agents. You can use agents which are more expensive, less expensive. We also plan to use open source model. At the moment, we're using front-end model, which means a bit on the expensive, but as I said, we are willing to give credits. So this all agentic form verification does all of it together. And you start by the design hardening. I think that's probably one of the most interesting things, that it gives you a better design. It starts with a white paper and it tries to see what are you covering. And the better documentation you have on the code, it will do a better job. And it will find more informal properties and it will find more formal properties. Questions so far? Because then I'm going to dive into examples of solidity, but I actually don't need you to understand solidity well. But question about the AutoProver so far. It's essentially, yeah.
Sorry, how are we fuzzing? Are we fuzzing the formalization, like the formalization step, and how are we doing the fuzzing?
The fuzzing at the moment,
Solution.
we're using Foundry, which is state-of-the-art fuzzer for smart contract. We plan to use Cargo fuzz later and Crucible for Rust. So we plan to use, we don't plan to develop our own fuzzer. We plan to use, but we can use, of course, AFL fuzzer. We can use all existing fuzzer. Also in the formification, we use open source formification. So to approve Lean 4, maybe we'll use Verus or Kani. So yeah, or CBMC. It's an agentic tool that calls other tools. And I should say, John Thoman is the main developer. It's very agentic. And also it has good feedback. So if you don't like it, you can tell it, and for example, it finds bugs and they're not real, you can tell it, and then the next time you'll try to refrain from giving these bugs. So it's learning thing from it. But it doesn't innovate on the fuzzing or formalification or other. But what it's good at is understanding actually where the formalification of fuzzing is good. So it's trying to leverage the properties to where having a fit with the underlying technology. But it's almost agnostic. In fact, you see the way it does fuzzing and it does formalification. There are not big difference between them. Because from the way the tool is looking, this is called a verification agent. The only difference is fuzzing does something on one input, and formalification does things on all input. Okay? Get it?
Got it.
Okay.
Thank you.
Okay, so I'll show you two examples. I will wrap up. So one of them is toy example, and the other one is real example. I encourage you to try other examples. I saw people actually using it in bug bounties. It's fantastic. The more you use it, the better. And as I say, you don't even need to use it on smart contract. You use it on any code that it makes sense. So this is an example If you're not familiar with Solidity, don't worry. You can think about it like a class. This is a counter. It has a very obvious bug that you see you're not using the parameter. I'm sure any tool can find this bug, but the idea is this is just to leverage the capability of this tool. So you see that what happened, there is some kind of interaction with the user, especially in the informal level. Okay, you have all these informal properties, and you see that here in the informal properties, it finds these informal properties. And this is where you need to interact, and this is where your feedback is the most important. This is where your design is going to be very useful. So you see here it found these properties about the code. It leverages properties of the code. By the way, it can do it even before the code is written. And also, interestingly, it can help you write new code because you can actually, with the properties, it can enforce these things. So in fact, it can generate code for you. And you see here that it's find the properties. You can talk with it. You see, you can ask it to explain. It's explained the properties, and then you can refine the properties. It's basically help you refine the properties, and then you get all these properties, and then it formulates it. It formulates in our language, it's called Certora verification language, is a similar thing that we have seen earlier, that there is some kind of harness where you write some precondition, some assumption on the code, you write the code, and you write post-condition, like the assert that we have seen in the beginning of the lecture. So you see, this is the idea. And you see here, this is the formal spec. Okay, so this is in our own language, but you don't need to get it the idea. You see these rules. These rules are enforcing these harnesses. You write this property, you write the function here. So you see here, you write the function. You mass int is an integer which is mathematic because you don't want to enforce properties of the implementation. And then you see you write the function, and then you write a set. Okay, so you see that this is how we write specification, and this specification it tries to verify that. You see that it was able to verify 3 rules, and one of them is violated, so it means it was not able to mathematically verify that, and it gives you the counterexample. You see, it gives you the counterexample. Interestingly, in the Certora prover, I'll show you, we give the mathematical example in the same way that we see in CBMC, but a bit more readable. But here you see that it converts the counterexample to English. This is beautiful. This is what LLM is able to do for you. LLM is able to read the counterexample from our prover and convert it to English. It's beautiful. It's make it easier. You don't actually need to understand the details, and you don't even need to understand the details of the program instructions. It's able to tell you the thing. So you see this, the description. This you see the violation in our tool. You see it's a bit more readable than CBMC, but still it's hard. It's essentially like the output of a debugger. You see that you get all the values. It's interesting because Certora, we analyze the bytecode and we have to actually decompile it, but it still could be hard, especially if you are not the developer of this code. But we get much more understanding. You see, you get a description of the bug, and then in fact, it can tell you how to fix it, and you convert how to proceed. You see how it tell you can refine the property. Of course, this could be a bug in your code or bug in your specification. If it's a bug in the specification, you change the specification. If it's a bug in the code, you change the code, or later on you can ask the code to change it. Once you fix, and that's a very interesting feature, once you do the fix, you can validate the fix, and that's a very different from using tools like testing or fuzzing. It in fact gives you a guarantee that once you fix, the bug is fixed. So you see, in fact, it doesn't mean that there are no bugs, but at least mean that this property holds. So this is the idea. I wanted to show you one example of real code. So, and people have already applied to real code. So here you see that it's applied to a really interesting, it's not, I should say, it's not a running code. It's a testing code. So in fact, it didn't find a live bug. it finds a bug in a testing version of one of the most interesting protocol in the space of Web3. Of course, we anonymize it. Here you see that we ran the tool in totally automatic way. So in fact, we didn't, you see, and all these properties, it came with these 15 properties with the LLM. So the LLM came with these 15 informal properties. And you see the rule number 15 is translated into a rule. And you see that there is a real violation. And again, the violation means either bug in the code that has to be fixed, or a bug in the rule. And you see that it suggests the fix. It suggests the fix. And in fact, it suggests the fix in the code. And once you change it, it's in fact it is guaranteeing that this fix, the rule is formally verified after you insert the fix. So let me just summarize. Thank you, and sorry I went a little bit over time. I think the question that you ask yourself, why now? Because as I said, formal verification has been a long time. So I think this is interesting, especially if you look back to this 78 paper saying why formal verification will never work. AI is making formal verification necessary because of the ideas that there are these bugs, and the only way to prevent these future bugs is in fact with given a proof, okay? But also AI makes formal verification much easier because it helps tools, whether it's tools based on proof assistant, whether tools that based on program verifier, it helps tools. It also helps understanding. You saw that we can digest the result of formal verification easier. We can make the formal verification apply to much more complex code. So we think that in fact it's a win-win situation. I could say, and actually people understand it in the LLM, formal verification also make the LLM better in many ways, because the formal verification can help the LLM in sort of focusing them on a real thing. Because I mean, you think about LLM is a very optimistic. Formal verification is like a pedantic lawyer, which actually prevent corner cases. So I think this is why they work together. So to summarize, we have this tool that we released. There is a landing page for it. I encourage you to use it. And as I said, we are giving credit for you to use it. This tool is doing auditing for arbitrary code. It's also doing fuzzing for Solidity and for Solana. It does formal verification for Solidity now, but Rust is coming, and we plan to add other support. It's the auditing itself is not open source, but the formal verification, testing, and everything else, the design hardening is all open source. It's written in Python with some part in Rust. We encourage contribution, and please try it. And I'm happy to answer more questions. Other questions?
Yes, Professor. How are we using just pure LLMs to drag down our specification into like natural language specification in the first step? Like you showed, there were lots of natural language specification that were written by the LLM itself. So are we using just a plain LLM to do this, or like how are we just trying to do all the assumptions of the code? Like what's the original spec that all these natural assumptions come from?
Right. So if you saw, if I go back, wait a second. So this spec here came purely from the design document, and it's beautiful. And the reason that the LLM was doing so good is because these protocol, they did very good job in the white paper. So in fact, if you have good white paper, LLM, the better your documentation is. I mean, I don't have any statistical, and this tool is new, but it came with these 15 properties because the team has done a very good job in the white paper. So if you have a good design, the LLM, of course, it's also the case is what are you developing? Are you developing a software that somebody else developed before you? So the LLM is better. If you are developing something unique, like if you're taking a sorting algorithm, the LLM will do an amazing job because sorting is something that we understood. But if you take the next very, very complex system that nobody did, it will be hard for the LLM. And then you'd have to help it. In the case of the AutoProver, we think that the best way to help is good design. If you have good design, the LLM is already doing it. But you can enter it in your own. You can enter, I suppose it gives you these 15 properties and you don't like. You start talking to it. It's almost like talking to a human. You will see. It's very, very agentic. So when you start using with the AutoProver, you learn to, it's very, very, at least in the Informal, it's very interactive. You can tell it, and in fact, it learns, it has loops, it has a lot of things. So you can interact with it. So if one of these properties are, and you can also challenge it, and it's interesting. You can ask it, why do you came up with property 14? And you try to explain. And it's very interesting. So, and the more you challenge it, it's like a human. It gets better. Okay, are you sure? You ask it a question like, "Are you sure?" And weird enough, it sometimes helps. It's also, I need to warn you, it's sometimes undeterministic. Sometimes you run it twice, you can get different results because this is the nature of LLM. That is, and that's the beauty of LLM, unlike the Certora or formalification, which is very deterministic. And but yes, but the bottom line, more your design is, the better your design is, we think it's probably fewer iterations. But yeah,
And
you can help it in any level. You can help it. You also can help with formal spec. You can help, but we think that the earlier you interact, the better.
okay. And also just my last question, sorry for all these questions, but is
No,
the
it's not
Certora
sorry.
prover
Thank you for the question. Okay.
the prover itself, is it using some in-house SAT solver or something, or are we using something like Z3 or CVC5 or something like that to as a core of the prover itself?
So the prover itself, we don't have our own in-house, although I should say that at this point, Z3 has done so many things for us, so we can call it our in-house, but we have also support for CVC5, for Yikes, for Bitsula, and a lot of these teams help us because we have so many examples. So we don't have in-house, but I think we have support for almost probably most of the SMT. And also some code, weird enough, it runs different solvers on different part of the code. So basically, because it will figure out that this part of the code is better for this and this kind of part of the code than me. And even on the same piece of code, it can take different branches and take them. So because we are running on complex low level code, so we are running different things, and we are running multiple portfolio solvers, and we're also trying to understand which one to use on which code.
Got it. Thank you. Final. Is there any like GitHub open source repo or somewhere where I can read it?
Yeah. You should Google because I cannot, but they are both. They are the GitHub source for the Certora Prover. There's the GitHub source for the AutoProver, and yes, and we accept contribution. Obviously, the Certora Prover is a very complex code, many hundreds of lines. The AutoProver is much simpler, but yes, we accept contribution on everything. And yeah, we love to have contribution. And as we say, we also integrated Foundry, which is open source. I'm sure they will love to have contribution. And we will love to integrate as many technology as possible to make this usable.
Thank you.
Thank you, everybody. Thank you for helping. Thank you for coming.